Hello, in this lecture we find out the area of the green shape. In the drawing we have a quarter circle, AOP is a quarter circle. We know that side OB equals to 2 units in its length, and line segment AD equals to line segment DO. In addition, we know that this is angle DCB that is equals to 90 degrees in size, and our mission is to find out the area of this green shape. The green shape is actually a right green triangle DCB. Therefore, our mission is to find out the area of the green right triangle DCB. So first of all, we know that AOB is a quarter circle. Therefore, angle AOB equals to 90 degrees in its side. This angle is a right angle. In addition, because of the fact that AOB is a quarter circle, sides A, O, and OB, they are both the radii of the circle, and therefore they are equal to each other. But side OB equals to 2 units. That is to say, the radius of this quarter circle equals to 2 units, and side AO, that is also the radius of the quarter circle, it is equals to 2 units. So AO equals to 2. It is given as a question that AD equals to DO. So if we define the length of AD as x, then AO must be also, then DO must be also equal to x because they are equal to each other. So AD plus DO equals to AO. Okay. Repeat again, AD plus DO equals to AO. So AD that is x plus DO that is also x equals to AO. Or x plus x equals to AO, but AO equals to 2, therefore x plus x equals to 2. X plus x is 2x, so 2x equals to 2. We divide this equation by 2 and get that x equals to 2 over 2, that is 1. So AD that is equal to x, according to our definition, it is equals to 1 unit in its length, and DO that is also equals to x, is equals to 1 unit in its length. In the next step, we do a construction. That is to say, we complete this quarter circle to a circle. We actually completed this quarter circle to a circle. In the next step, we'll extend the radius BO by a straight line until it touches the circle at this point. MO as a radius, it is absolutely a straight line. We extended the straight line BO by straight line, therefore the result must be a straight line. We define the touching point of the extended radius BO with this circle, this point as point P. Again, we extended the straight line BO by straight line, therefore the result BP must be also a straight line. So if we focus on the upper side of this straight line BP at point O, here the sum of the angles must be equal to 180 degrees according to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BP at point O? We have this angle that is 90 degrees plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its side. We know that BP is a straight line, but BP is a straight line that touches the circle at 2 points, point B and point P. And any straight line that touches the circle at 2 points, it is defined as a chord. So BP is a chord, but BP is a chord that passes through the center of the circle, that is to say from point O, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore BP is the diameter of the circle. So I write it down. So actually found out that BP is the diameter of the circle. In the next step, we do a construction, that is to say, we will extend side CD by straight line until it touches the circle. The question is where the extended side CD will touch the circle. We will assume that the extended side CD will not touch the circle at point P, but in any other point. For example, we will assume that the extended side CD we touch the circle at this point that we define as point G. So by doing this construction, we can deduct peripheral angle BCG. This is peripheral angle BCG, and according to what is given us in the question, this angle is the right angle. So we have peripheral angle BCG that is the right angle, that is to say it is equal to 90 degrees in its size, and it is subtended on BG. BG is definitely not the diameter of the circle, because we know that the BP is the diameter of the circle. And from point B we have only one diameter to this circle. Again, from point B we have only one diameter to this circle, that is the diameter BP. And therefore BG cannot be the diameter of the circle. Repeat again, BG cannot be the diameter of the circle. So we have peripheral angle that is equal to 90 degrees in its size, and still it doesn't subtend on the diameter of the circle, but it is subtended on BG that is not the diameter of the circle. But that is a contradiction to rule 5. Repeat again on rule 5, according to rule 5, any peripheral angle that is equal to 90 degrees in its size must be subtended on the diameter of the circle. We have here peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in its size, and it is subtended on MN, that is the diameter of the circle. So according to rule 5, any peripheral angle that is equal to 90 degrees in its size must be subtended on the diameter of the circle. But here, we actually found out in our drawing peripheral angle BCG that is equal to 90 degrees in its size, and still it doesn't subtend it on the diameter of the circle. This contradiction to rule 5, because peripheral angle BCG must be subtended on the diameter of the circle, because it is a right angle. So in order to avoid contradiction to rule 5, we must conclude that the extended side CD will touch the circle at point P and only at point P, and not in any other point. So we have here peripheral angle BCP that is equal to 90 degrees in its size, and it's subtended or called BP, that is the diameter of the circle. So we don't have any more contradiction to rule 5. Okay. In the next step we will find out what is the definition of line segment OP. Line segment OP starts from point O, that is the center of the circle, and that's at point B, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OP is the radius of this circle, that is equal to 2 units in its length. In the next step, I'll copy the right triangle PDO in a new page, and we'll implement the Pythagoras theorem on this right triangle PDO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle PDO that the common from the original drawing. According to the Pythagoras theorem, in this right triangle PDO, dP square equals to dO square plus OP square. So I write it down. According to the Pythagoras theorem, in this right triangle PDO, dP square equals to dO square plus PO square. The hypotenuse dP is the missing side, so we'll leave it as it is. So dP square equals to dO square. dO is 1, therefore dO square is 1 square, that is 1, plus PO square. PO is 2, therefore PO square is 2 square, that is 4. So in total, if we found out that dP square equals to 1 plus 4, that is 5. dP square equals to 5. We take a root out of this equation and finally get that dP equals to the square root of 5 units in its length. dP equals to the square root of 5 units. Sin dP equals to the square root of 5 units in its length. In the next step, we'll focus on the right triangle DPO. In this right triangle DPO, we'll define angle DPO. This angle is theta. So in the right triangle DPO, this angle equals to theta, this angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we'll focus on the right big triangle PCB. The right big triangle PCB, this angle equals to theta, this angle equals to 90 degrees. Therefore, the missing third angle here must be equal to 90 degrees minus theta. In the next step, we prove that the right big triangle PCB is similar to the right small triangle PDO. So write it down. We prove that the right big triangle PCB is similar to the right small white triangle PDO. So why the big triangle PCB is similar to the small triangle PDO? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle PCB in the right big triangle PCB, and it is equal to this angle, this is actually angle DOP, in the right small triangle DPO. Repeat again. Angle PCB in the big triangle PCB equals to angle DOP in the small triangle DPO. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It is a common angle that belongs to both triangles. So we can write down that angle theta equals to itself as a common angle that belongs to both triangles. If we relate to angle theta as it belongs to the big triangle PCB, it will be defined as angle PPC. And it is equal to itself. So if we relate to angle theta as it belongs to the small triangle, on PD it will be defined as angle DPO. So actually, this equation means that angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually, this is angle PBC in the big right triangle PCB, and it is equal to this angle, that is actually angle PDO in the right small triangle PDO. Repeat again, found out actually that angle PBC in the big right triangle PCB equals to angle PDO in the right small triangle PDO. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually found out that all the triangles of the right big triangle PCB are correspondingly equal to all the triangles of this right small triangle PDO. Therefore, the right triangle PCB is similar to the right small triangle PDO according to angle similarity rule. So I write it down. We actually found out that the right big triangle PCB is similar. This is the sign of similar to the right small triangle PDO according to angle similarity rule. And for the fact that the right big triangle PCB is similar to the right small triangle PDO, we conclude that the following relationship exists between their sides. That side PD in the small triangle PDO over side PB in the big triangle PCB equals to side DO in the small triangle PDO over side CB in the big triangle PCB, and it is also equals to side PO in the small triangle PDO over side PC in the big triangle PCB. So actually found out that according to equation 1, PD over PB equals to DO over CB equals to PO over PC. Okay. PD is equal to 5 over PB. PB is the diameter of the circle, that is equals to 2 plus 2, that is 4. PB is 4, and it is equals to DO. DO is 1 over CB. CB is the missing side, so we leave it as it is. And it is also equals to PO. PO is 2 over PC. PC in total equals to the square root of 5 plus DC. Repeat again, PC in total equals to the square root of 5 plus DC. So in conclusion, we should have found out that according to equation 1, square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two expressions are equal to each other, therefore we get equation 1 from those two expressions that are equal to each other. So according to equation 1, we get that square root of 5 over 4 equals to 1 over CB. So here we first multiply this equation 1, and we get that according to this equation 1, square root of 5 times CB equals to 4. Here we divide this equation 1 by square root of 5, and you get that according to this equation 1, CB equals to 4 over square root of 5 units in its length. So we should found out that side CB equals to 4 over square root of 5 units in its length. We continue to focus on the log equation, and here this log equation, this first expression equals to the further expression, so we get equation 2 from those two expressions that are equal to each other. So according to equation 2, we get that square root of 5 over 4 is equals to 2 over square root of 5 plus DC. This is equation 2. Here we cross multiply this equation 2, and you get here that according to equation 2, square root of 5 times square root of 5 plus DC equals to 4 times 2, that is 8. So here we'll open the brackets on this side of this equation 2, and get that according to this equation 2, square root of 5 times square root of 5 is 5, and square root of 5 times DC, square root of 5 DC is equals to 8. Here subtract 5 from this equation 2, and get that according to this equation 2, square root of 5 times DC equals to 8 minus 5 is 3. So here we divide this equation 2 by square root of 5, and finally we get that according to this equation 2, DC equals to 3 over square root of 5 units in its length. So actually this is side DC, and it is equals to 3 over square root of 5 units in its length. Our mission is to find out the area of this green shape. The green shape, actually, it is the right triangle DCB. And therefore, actually, we'll find out the area of the green right triangle DCB. Repeat again, the area of the green shape equals to the area of the green right triangle DCB. So what is the area of the green right triangle DCB? Actually, we know that the area of any triangle equals to the base of the triangle times the height to the base over 2. So the area of the green right triangle DCB, that is the area of the green shape, equals to the base of the triangle times the height to the base over 2. We choose the base of this green right triangle DCB as DC. And what is the height? The height must create 90 degrees with the base DC. Here CB creates 90 degrees with the base DC because this angle equals to 90 degrees. So the height is CB over 2. DC is 3 over square root of 5. The base DC is 3 over square root of 5 times CB. CB is 4 over square root of 5. Again, CB is 4 over square root of 5 divided by 2. So here we have 3 times 4 is 12 over square root of 5 times square root of 5 is 5 divided by 2. 12 over 5 over 2 is equals to 12 over 5 times 2. So it is equals to 12 and 5 times 2 is 10. So the area of the green shape equals to 12 over 10 square units. Here we divide this number both the numerator and the denominator of this number by 2, and we get that 12 over 2 is 6 and 10 over 2 is 5. So actually we found out that the area of this green shape equals to either 6/5 square units, or in terms of numbers, the area of this green shape equals to 1.2 square units. Okay, so in the next step, I'll summarize the lecture. In this lecture, I found out the area of this green shape. So, in the drawing, we have a quarter circle. AOB is a quarter circle. In addition, we know that side OB equals to 2 units in its length, and line segment AD equals to line segment DO, and this is angle DCB. That is the right angle. I repeat again that our mission is to find out the area of this green shape. So, in the first step, we know that this is angle AOB, and AOB is a quarter circle, and therefore this angle AOB must be equal to 90 degrees in its size. Repeat again. This angle AOB must be equal to 90 degrees in its size because AOB is a quarter circle. In addition, because of the fact that AOB is a quarter circle, it means that sides AO and OB, they are both the radii of this quarter circle, but we know that side OB equals to 2, therefore the radius of the quarter circle equals to 2 units, and therefore the radius AO also equals to 2, so AO equals to 2. We know that AD equals to DO according to what is given in the question, so if we define the length of AD as x, then DO must be also equal to x because they are equal to each other. AD plus DO equals to AO. Again, AD plus DO equals to AO. So AO equals to AD, that is x, plus DO, that is x. So AO in total equals to x plus x, that is 2. But AO in total equals to x plus x, that is 2x. So 2x equals to AO, but AO is 2, therefore 2x equals to 2. We divided the equation by 2 and finally found out that x equals to 2 over 2, that is 1. So AD that is equal to x equals to 1, and DO that is also equals to x is equals to 1 unit in its length. Okay. So here in the next step we did a construction. That is to say, we completed this quarter circle AOB to a circle, and then we extended the radius BO by a straight line until it touches the circle. We define the touching point of the extended radius BO with this circle. This point is point P. BO is a radius, it is absolutely a straight line. We extended the straight line BO by a straight line, therefore the result BP must be also a straight line. So BP is a straight line. If we focus on the upper side of the straight line BP at point O, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of BP at point O? We have this angle that is a right angle plus this missing angle. In total they must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. Okay. So we shall found out that BP is a straight line, but BP is a straight line that touches the circle at 2 points B and P, and therefore the BP is a chord. But BP is a chord that passes through the center of the circle, that is to say from point O, this point O, and we note that any chord that passes through the center of the circle must be the diameter of the circle. Therefore BP is the diameter of the circle. So note here that BP is the diameter of the circle. In the next step we did a construction. Actually we extended side CD by straight line until it touches the circle. The question is where the extended side CD will touch the circle. We'll assume that the extended side CD will not touch the circle at point P, but in any other point, that is to say, for example, we'll assume that the extended side CD will touch the circle at point G. So by doing this construction, we created here peripheral angle BCG, and this peripheral angle BCG equals to 90 degrees in its size according to what is given as the question. And the peripheral angle BCG is equal to 90 degrees in its size is subtended on BG. Again, peripheral angle BCG that is equal to 90 degrees in its size is subtended on chord BG. But chord BG is definitely not the diameter of the circle. Why? Because of the fact that from point B we have only one diameter, that is the diameter BP. In any circle, from any point, you can draw only one diameter. And we have already the diameter BP. And therefore, any other chord that exists from point B cannot be the diameter. Therefore, BG is not the diameter of the circle. So we have peripheral angle BCG that is equal to 90 degrees in its size. This is subtended on BG that is not the diameter of the circle. This is a contradiction to rule 5. I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must be subtended on the diameter of the circle. We have peripheral angle MAN that is equal to 90 degrees in its size, and it's subtended on MN that is the diameter of the circle. And therefore, according to rule 5, because of the fact that peripheral angle BCG is equal to 90 degrees in its size, it must be subtended on the diameter of the circle. But it is subtended on BG that is not the diameter of the circle, therefore we have a contradiction to rule 5. In order to avoid the contradiction, we can conclude that our assumption that the extended side CD touches the circle at point G is not correct, and we must conclude that the extended side CD touches the circle at point P and not in any other point. In this way, we get that we have peripheral angle BCP that is equal to 90 degrees in its size, and it is subtended on PB, that is the diameter of the circle, exactly according to Rule 5. Okay? So, here we have what is the definition of line segment OP. Line segment OP starts from point O, that is the center of the circle, and then at point P, that is the point of the circle itself. So, therefore, this is exactly the definition of a radius. Therefore, OP is the radius of the circle that is equal to 2 units in its length. In the next step, I copied the right triangle PDO in a new page and we implemented the Pythagoras theorem in this right triangle PDO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle PDO is dp, therefore the square of the hypotenuse is dp square, and dp square must be equal to do square plus po square. dp is the missing side, so leave it as it is. So dp square equals to do square. Do is 1, therefore do square is 1 square, that is 1, plus po square. Po is 2, therefore po square is 2 square, that is 4. So in conclusion, total function found out that dp square equals to 1 plus 4, that is 5. dp square equals to 5, we took out of this equation and finally found out that dp equals to the square root of 5 units in its length. This is side dp, and it is equal to the square root of 5 units in its length. In the next step, we focused on the right triangle PDO, and we defined this angle DPO as theta. So in the right triangle DPO, this angle equals to theta, this angle equals to 90 degrees, therefore the missing third angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, we focused on the right big triangle PCB. On the right big triangle PCB, this angle equals to theta, this angle equals to 90 degrees, therefore the missing third angle must be equal to 90 degrees minus theta. In the next step, we proved that the right big triangle PCB is similar to the right small right triangle PDO. Again, proved that the right big triangle PCB is similar to this right triangle PDO. So why the right triangle PCB is similar to the right small triangle PDO? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles. So we can find out that angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I can prove that all the three angles in the right big triangle PCB are correspondingly equal to all the three angles in the right triangle PDO. Therefore, the right triangle PCB, the right big triangle PCB is similar to the right small triangle PDO according to angle similarity rule. And repeat again, we found out that the right big triangle PCB is similar, this is the sign of similar, to the right small triangle PDO according to angle similarity rule. And from the fact that the right big triangle PCB is similar to the right small triangle PDO, we conclude that the following relationship exists between their sides. We conclude that side PD in the small triangle over side PB in the big triangle equals to side DO in the small triangle over side CB in the big triangle, and it is equals to side PO in the small triangle over side PC in the big triangle. PD is equal to 5, PB is 4, DC is 1, CB is the missing side, so we leave this it is, PO is 2, and PC is equal to 5 plus DC. So according to equation 1, we found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two expressions they are equal to each other, and therefore we get equation 1 from those two expressions that are equal to each other. So according to equation 1, we found out actually that square root of 5 over 4 equals to 1 over CB. This is equation 1. If of course multiply this equation and equation 1, we finally found out that according to this equation and equation 1, square root of 5 times CB equals to 4, Here we divided this equation 1 by square root of 5 and finally found out that CB equals to 4 over square root of 5 units its length. The missing side CB equals to 4 over square root of 5 units its length. We continue to focus on the long equation 1. In this long equation 1, this the first expression equals to the third expression. So we get the equation 2 from those two expressions that are equal to each other. So according to equation 2, we should find out that the square root of 5 over 4 equals to 2 over square root of 5 plus DC. Repeat again. According to equation 2, we should find out that square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here we cross multiply this equation 2 and finally found out that according to equation 2, square root of 5 times square root of 5 plus DC equals to 2 times 4, that is 8. Here we open the brackets on this side of this equation 2 and finally found out that according to this equation 2, square root of 5 times square root of 5 is 5, and square root of 5 times DC, square root of 5 times DC. And it is equals to 8. Here subtract 5 from this equation 2 and finally found out that square root of 5 times DC equals to 8 minus 5, that is 3. Here we divided the equation 2 by square root of 5 and finally found out that the missing side DC equals to 3 over square missing side DC equals to 3 over square root of 5 units in its length. So this is the missing side DC, and it is equals to 3 over square root of 5 units in its length. Our mission is to find out the area of this ring shape. The ring shape is actually the right triangle DCB. So our mission is to find out the area of this right ring triangle DCB. We know that the area of any triangle equals to the base of the triangle times the height of the base over 2. The base of the right ring triangle DCB, we choose the base as DC, and the height is CB. The height is CB because it creates 90 degrees with the base CB. Okay, again, we choose the base as DC and the height as CB, so the area equals to the base DC times the height CB over 2. DC equals to 3 over square root of 5 times CB equals to 4 over square root of 5 divided by 2. Here 3 times 4 is 12 and square root of 5 times square root of 5 is 5 divided by 2. So the area of the ring shape equals to 12 over 5 over 2. 12 over 5 over 2 equals to 12 over 5 times 2. So it is 12 and 5 times 2 is 10. So the area of the ring shape equals to 12 over 10. Here we divided both the numerator and the denominator of this expression by 2 and found out that 12 over 2 is 6 and 10 over 2 is 5. So in total we found out that the area of this ring shape equals to either 6/5 square units, or in terms of numbers, the area of this ring shape equals to 1.2 square units. Okay, thank you very much.